Welcome to this module, and this is in continuation with our last module. So, the idea here is that we are looking at the summary of integrated circuits, MOSFETs, op amps and their applications. The reason of revising this particular slide is that we can use the knowledge that we acquire either in the last course or in the present modules for practical applications of op amps. So, to understand the op amps, we need to understand the theory of op amp, right, and that is why we are looking at the characteristics and the parameters of the op amps. So, in the last module what we have discussed oscillators, right, and in oscillators we have seen that there are several kind of oscillators depending on the waveforms, depending on the frequency, depending on the components used, depending on the feedback, and then we have also seen the Bar-Coshine criteria, right, where we require the mode of A into beta, that is gain into feedback factor should be greater than or equal to 1, or and actually not or, it is and the phase shift, that is the output signal that is fed back to the input, the phase of that output signal that is fed back to the input should match the input signal phase, right. That means that feedback phase should be 0 or 360 degree. Then after that we have seen RC oscillators, right. So, and RC oscillators we have seen RC phase shift oscillator, how we can phase shift 180 degree signal from the output of the inverting amplifier using RC network, and then we have also seen a Wien bridge oscillator where there is no need of phase shift, and that R and C, which are frequency sensitive arms, by changing the value of R and C we can change the frequency, right. So, we have also discussed that if I go and use L and C instead of R and C, that means inductor and capacitor, then the oscillators can be used for high frequency applications, right. So, what are high frequency applications and how we can design a LC oscillator. So, let us see today how we can design LC oscillators. So, if you see on the screen, what you see that the oscillators which uses the element L and C to produce oscillations are called LC oscillator. The circuit uses L and C is called tank circuit or oscillator circuit, which is an important part of LC oscillator. The circuit is also referred to as resonating or tuned circuit, right. So, you can see on the left side L, inductor and capacitor, this is a circuit used for oscillation in the LC oscillators. These oscillators are used for high frequency range, like we discussed, from 200 kilohertz to few gigahertz. Now, since the frequency range is high, these oscillators are also referred as RF or sources for RF energy or sources of RF energy. LC tank oscillator circuit consists of L and C connected in parallel as shown in the figure. Let the capacitor be initially charged from a DC source which polarity as shown in figure. So, suppose a DC source is there and we are charging the capacitor in the polarity shown in figure, what will happen, right. So, when the capacitor discharges, the energy that is stored in this capacitor, right, when the capacitor charges, let us say first when it charges what happens. So, when it charges, the energy stored in the capacitor is electrostatic energy, right, and when such a capacitor is connected across a inductor, then what will happen, the capacitor will start discharging. So, when it starts discharging through L, right, the magnetic field gets set up around the inductor and thus inductor starts storing the energy, right. So, when capacitor is fully discharged, maximum current flows through the circuit. At this instant, all electrostatic energy is converted to magnetic energy or is stored as a magnetic energy in the inductor. Now, when the magnetic field around L starts collapsing, what will happen? As per Lenz's law, this charge charging the capacitor with the opposite polarity, right. So, now when this starts collapsing, the capacitor will start charging in the opposite polarity, right, making lower plate more positive and upper plate negative, right. Now, again after some time, when capacitor fully gets charged, it will start discharging and with the opposite polarities as compared to its initial polarities, right. Initially it was plus on the top plate, minus on the bottom plate. Now, it is plus on the bottom plate, minus on the top plate. So, now it is discharging with the opposite polarity compared to its initial polarity, and the entire magnetic energy gets converted to electrostatic energy in capacitor. Wow, that is earlier we have seen, and now the electrostatic energy when it starts discharging is converted to magnetic energy once again, right. So, it is from when inductor discharges, it is electrostatic energy that is stored in the capacitor, where the capacitor discharges in the magnetic energy that is stored in the inductor, right, and this keeps on continuation until, and because of this what will happen, that every time when this transfer of energy occurs, right, there is a loss, and this loss causes the amplitude of the oscillating current decreasing. See this loss because of the inductor charging and capacitor discharging and capacitor charging and inductor discharging, and again this goes on continuation. What happens every time this discharge and charging happens, there is a loss in the circuit, and this results in the lower oscillation, amplitude of oscillations gets down as you can see here, and current keeps on decreasing, right. So, actually we get an exponential decay as you can see from the figure oscillations, and these are called damped oscillations. These are called the damped oscillations, right. So, such oscillations stop after some time, of course, right. So, initially you can see, and then after some time you can see that these oscillations are on the edge of dying, right, on the edge of dying. So, what we can do, right, what we can do. So, in LC oscillator the transistor amplifier supplies this loss of energy at proper time. So, if I have a transistor amplifier, then the energy that is lost during the charging and discharging of the inductor and capacitor, right, can be compensated using the transistor amplifier, right. The LC circuit along with transistor amplifier can be used to obtain oscillators called LC oscillators. Due to supply of energy which is lost, the oscillation gets maintained and hence called sustained oscillation or undamped oscillation. Here the frequency of oscillation generated by LC is given by f equals to 1 by 2 pi root LC, right, where L is in Henry and C is in Farad. Depending on the type of tank circuit, the LC oscillators are classified into two categories. One is called Colpitts oscillator, another one is called Hartley oscillator. Now, LC or circuit forms a feedback network, while an op amp or FET or BJT can be active device. The figure shows here, you can see the left side of the figure, right, shows the form of LC oscillator with gain of amplifier AV, right. The amplifier output feeds the network consisting of impedances Z1, Z2 and Z3. We will assume that active device with infinite input impedance such as FET, right, or op amp, then the basic circuit can be replaced by linear equivalent circuit. So, if I want to replace this by linear equivalent circuit, I can draw like this, right. See its input impedance is infinite, right, and amplifier provides a phase shift of 180 degree because it is a inverting terminal we are applying the signal, right, while the feedback network provides a phase shift of 180 degree. So, here the feedback network that we are designing or we will be using will provide another phase shift of 180 degree to satisfy the required oscillation, that is that total phase shift should be 360 degree. So, if we analyze this amplifier stage, what we get is that I equals to minus AV Vi upon RO ZL, RO plus ZL, you can see from here, right, and using the equation, right, what we can get, gain of the amplifier VO by Vi equals to AV ZL upon RO plus ZL, where A is the gain of the amplifier stage, right. So, further when we analyze, what we get beta equals to Vi by Vo, and that will be nothing but Z1 upon Z1 plus Z3 in terms of minus, that is 180 degree phase shift. So, A beta would be this formula. So, this is the required loop gain, ZL can be written as Z1 plus Z3 parallel to Z2, you can see here, right. So, if we substitute, what we get? We substitute, then finally when you solve this equation, what you get? You get is that your A beta, right, will be AV x1 by x2, AV x1 by x2, and AB must be positive, right. Here what we see is minus A into beta, the last line we see that when we derive this, when we solve this, we get minus A beta equals to AV x1 by x2, but it cannot be minus, right, it should be minus AB should be positive and must be greater than or equal to unity, right. We have seen that it is bar question criteria. So, as AB is positive, minus A beta will be positive only when x1 and x2 will have same sign, right. If an x1 and x2 have same sign, then only minus A beta can be positive, right. This indicates that x1 and x2 should be of same type of reactances. You see here again minus A beta equals to AB into x1 by x2, but minus A beta should always be greater than or equal to 1. That means, x1 and x2 should be same reactances, right, should be have same type of reactances. So, either we can use x1 and x2 as inductive, or we can use x1 and x2 as capacitive, right, either x1 and x2 as inductive or capacitive. While we can also say that x3 equals to minus x1 x2. So, that means that if x1 and x2 are capacitive, x3 should be inductive, and if x1 and x2 are inductive, x2 should be x3 should be capacitive, right. So, either x1 and x2 are inductive, then x3 is capacitive, x3 if x1 and x2 are capacitive, then x3 should be inductive, right, vice versa. So, if x1 and x2 are inductive and x3 is capacitive, it is Hartley oscillator, and if x1 and x2 are capacitive and x3 is inductive, it is Colpitz's oscillator, right. We have seen this. Now, if I want to design Hartley oscillator, then this is the way to design Hartley oscillator. This is a tank circuit, as we know, right, and this can be implemented by using 2 inductors and 1 capacitor. Each section produces a phase shift of 180 degree, right, each section produces 180 degree, and hence it produces a sine voltage, right, it produces a sine wave voltage. Here we know that the FO equals to 1 upon 2 pi under root of L equivalent into C, right, because there are inductors L1 and L2. So, what is L equivalent? L equivalent is nothing but L1 plus L2 plus 2m or L1 plus L2. To generate oscillation from this circuit, the amplifier must be selected greater than or least equal to the ratio of 2 inductances, right. That means that the amplifier gain should be at least equal to L1 by L2. So, it should be greater than or equal to, okay, it should be greater than or equal to the ratio of L1 and L2. If there is a mutual inductance, that exists between L1 and L2, right, because of the common core, then the gain becomes L1 plus m by L2 plus m. So, what is the advantage of this oscillator? The advantage is that instead of 2 separate coils as L1 and L2, a single coil of a bare wire can be used and the coil can be grounded at any desired point. Second is, by using variable capacitor or by making core movable, frequency of oscillations can be varied, right. That is another advantage. Amplitude of the output remains constant over the frequency range, and finally, very few components are required, right, for including either 2 fixed inductors or a tapped coil. But there are few limitations. What are limitations? That it cannot be used for low frequency oscillation, right, since the value of inductors becomes large and size of the inductor becomes bulky, right, it is obvious, correct. The harmonic content in the output of this oscillator is very high, and hence it is not suitable for application which requires pure sine wave. So, there is a harmonic oscillations that limits its use for pure sine wave. Colpitz's oscillator. Next is a Colpitz's oscillator. Here we are using 2 capacitors and 1 inductor. In this oscillator, like we see here in the tank circuit, there are 2 capacitors, right, and 1 inductor. So, here the op amp provides the basic amplification needed with the feedback network. In the given circuit, op amp is connected as inverting amplifier with a high gain as compared with transistor circuit. When the power supply is given to the circuit, there is no signal, right, initially there is no signal, but a small noise voltage are amplified with the help of amplifier, op amp amplifier. This makes the both capacitors to charge and discharge, right. The part of signal across the capacitor C2 is fed to the inverting amplifier, right, here it is fed back to the inverting amplifier and then amplified and keeps the network oscillating strongly, right. So, initially through the noise voltage we are amplifying the noise voltage with the help of amplifier, it is fed back to the tank circuit, and part of signal is fed back to the amplifier, and there is a strong oscillations which causes strong oscillations. Here we have same formula, but instead of L equivalent here we have C equivalent, and we know that C equivalent is nothing but C1 C2 by C1 plus C2. So, what are the applications of Colpitts oscillator? Colpitts oscillators are used for high frequency range and high frequency stability, right. It can also be used as a SAW resonator, that is surface acoustical wave resonator, used in microwave applications, mobile and communications, right, and these are used in chaotic circuits which are capable to generate oscillation from audio frequency to the optical band. The application area include broadband communication, spectrum spreading, signal masking, etc. So, this was the end of this particular summary of the oscillators, right. So, if you recall, we have just understood right from the indicator circuit quickly, right, then we went to op amp, its characteristics, then we saw few amplifiers, then we saw oscillators, right, and we also saw filters. Now, in the next module, or rather in the next lecture, we will see how we can design and implement circuits using operation amplifier. And like I said, slowly and gradually you will understand when you read from my earlier course till now, we are slowly and gradually increasing the tempo, right, we are increasing the tempo. The reason is that we should start from basic, right, understand the concept, grab it, and then move on to applying it. So, you will see in this particular applications of op amp, it is little bit complicated than the earlier practicals that we have seen in the last course, right. And finally, we are actually designing a signal conditioning device for measuring ECG as well as heart rate, right, and that is a really complicated project. So, let us see how we go further in the next lectures. I will see you in the next lecture. Till then, you just go through all the modules, right, keep your basic strong, right, refresh it, even you know it, it is always good to refresh, right. I will see you in next class. Till then, you take care.